last page. So, first question here is number 8. As the time it takes to do work decreases, what happens to the power? Well, power, of course, increases. If you are compacting the work that you're doing into a smaller amount of time, you're going to need more power to get it done faster, as opposed to doing it more slowly. Less power is required. It's running versus just walking. And actually, there was one student who I gave him half the credit here, because they said power decreases, it takes more power to run up the stairs than to walk, which was a perfect explanation of why power increases when the time is decreasing. And so I think that's just, take a moment and think about what it's trying to say, and because they were absolutely on the right track, just slightly missed it with the explanation. So that's what I was looking for here, is that the power does increase. Okay, the next one was to provide an example of Newton's first law of motion. A lot of students didn't actually give an example. They just wrote out the first law. An object in motion will stay in motion unless acted on by an outside force, and an object at rest will stay at rest unless acted on by an outside force. So I did give you 2 points if you could at least tell me what that first law was, but I really wanted to see an actual example. Here was a good one. Someone's sitting in a car and taking a sharp left turn, and their body wants to go straight, but and so the car's turning to the right, and so you're kind of like, and it's that Jello thing. Like, oh, we're going this way, we're going that way. And because your body actually wants to keep going straight, but the car that you're sitting in, here's you in the car, you want to keep going straight. The car goes this way, and so your body feels like it's being tugged the opposite direction, but actually you're just trying to go straight and the car's pushing on you. So that's a great example of inertia, which is our first law of motion. And then let's see, another one that was a good example here. I love this. If a soccer ball is kicked in a vacuum with no gravity, it will continue traveling. If, however, it were on a field, it would be brought to a stop by friction. So friction of the grass, gravity pulling it down so that it actually hits the grass and starts rolling across it. So that was a good one. One example is when a car comes to a stop and the passengers lean forward a little bit. Perfect. Very quick, succinct example showing inertia, which is that first law, Newton's first law of motion. The SI unit for mass, kilograms, of course. And then some folks were giving me an M. In an equation, we use an M as the symbol to represent mass, like in any of these equations. Whenever we see M in these equations, that does stand for mass, but the unit for mass, what we measure mass, you wouldn't say that you have a mass of 60 M. That doesn't make sense. Your mass is measured in kilograms. 60 kilograms is what your mass is. Okay? So there's a difference between the symbol, which is the thing that we put in the equation for short, and then the unit is what we actually are measuring it in. Let's see, relationship between work and energy. You must have energy to do work. Work is the change in energy. The more work is done, the more energy is used. Energy measures how much work can be done. That was kind of, on the edge, but it was still getting that relationship. I'm not sure about the word measures. I would say, well, really, it's a change in energy is equal to your work. Energy is known as the ability to do work. That was a good example. And then we get into an example of work being done. So in all of these examples, this one is a person carrying a backpack up the stairs, and I like that they notice that the backpack is being pulled up and you walk up the stairs, showing that force and the direction of motion are in the same direction, and these parallel arrows showing that. That was excellent. And then showing perpendicular arrows, the backpack is being pulled up, but you walk forward, and so that those are in different directions. So that was a perfect example here. And then I've got the crane lifting. and that crane is lifting an object. And then here, when the person lifts the box, that part, that act of lifting, that is going to be work. But then once they're just moving forward, that part would not be considered work. And so that's why I circled that, because that part right there is work. But the rest of it, what they've got here in their diagram, I think they're really just trying to say, before this happens, you have to lift the box. The person lifts and then carries it across. That's the part that's not work. Lifting, because that would be a force in the same direction as the object is moving, that would be work. That's really splitting hairs. Yeah, and then there were a few more very similar, lifting the object and then moving forward, pushing the box. So because you're like pushing, it looks like a big box or like a refrigerator or something, pushing that, the force applied in the same direction the object is moving, that's good. And then here, pushing against the wall, but the wall isn't moving. So you're trying to apply a force, but since the object isn't actually moving, no work is actually being done. So those were some perfect examples right there. And that is the end.